there, faithful AP Chem students. We are going to continue to talk about equilibrium. So we're exploring this idea of change in an equation, right? We're exploring this idea of change and how it gets us to our final state. So in the last video, this is where we ended. We talked about how we have this reaction, and then we were given a specific change to it. So one of the questions you're going to keep running into is, how do I know what my change is? Well, we haven't talked about that yet. In this problem, they just gave us a change and we used it, right? So we used it to get to this final amount here. And because of this arbitrary change, we get this final amount, and here we are. Now, the question is, how do we get to equilibrium from here? Since we just used a random amount of change, we don't know if we're at equilibrium or not. That's one of the things we have to figure out, okay? So the only piece of information they've given us on equilibrium is our K. If we go back a slide, you'll see here that they tell us that our K is equal to 16. That's the only piece they've given us, piece of information that tells us anything about where equilibrium is. So let's go forward a slide, back to where we just were, and we'll use this information that K is equal to 16 and see if we can't get ourselves to equilibrium. So first of all, let's figure out, are we at equilibrium? If we're at equilibrium, then we can take the amounts that we are, and we should be able to plug into that ratio, and our ratio is going to be equal to 16. So let's do that. We have our K, it's equal to our products raised to their coefficients, which is just 1, over our reactants raised to their coefficients, which is just 1. So we have 25 over 28 here. And I don't even have to do the division. I can see automatically that this is not equal to 16. It's less than 1, right? So whatever it is, it doesn't matter. It is not equal to 16. So if we ever have amounts and we plug them into our law of mass action, and we don't get a number that's equal to K, then we can't call this fraction K. We can't call this ratio K. What we call it is Q. Q means we're using the law of mass action, but we're plugging in positions that are not equilibrium positions. So in this case, Q is less than K. What does Q have to be? How does Q have to shift in order to get to K? So think about that. How does Q have to shift in order to get to K? What do products have to do? Do products have to get bigger or smaller? What do reactants have to do? Do they have to get bigger or smaller? So products have to get bigger, reactants have to get smaller. Our numerator has to get bigger, our denominator has to get smaller in order for this ratio to shift and become bigger and eventually get to K, right? So we know we're going to shift towards products. Our products have to get bigger, our numerator has to get bigger, our reactants or our denominator has to get smaller. Okay, so what's the change? If we start here, and this becomes our new initial change final, and this final is going to be at equilibrium, what is our change going to be? Well, we don't know, right? We actually don't know what this change is going to be. So we can start from here and move forward, or we can go back to our initial amount and move forward. It doesn't really matter where we start. What matters is that in the end, our ratio is equal to 16. So we're going to go through a couple different ways that you can solve this problem. For now, one of the ways you could do this is by using X as your change. So for example, we don't know what the change is going to be, but we do know it's going to use reactants, right? So we're going to use a negative X on this side. And since it's a 1-to-1 relationship, I can use negative X's and positive X's, and I don't even have to worry about multiplying them. And then I get final amounts: 4 minus X, 7 minus X, 5 plus X, 5 plus X. So these are my amounts at equilibrium. And then I can plug into my K equation. So K equals 16 equals 5 plus x to the first, 5 plus x to the first, over 4 minus x to the first, 7 minus x to the first. And then I can solve for x. Now, doing it this way is not super ideal because we're going to have to multiply through and use the quadratic equation at some point in time. So we're going to do one of these problems. We're going to walk it through from start to finish, but I want to work with K a little bit more before we actually have to do this. Okay, so let's work with K a little bit more before we get into using the variables. Okay, so a little bit more about what K means. So K is talking about, K can indicate the direction that our reaction has to go. We just saw that. We can talk about what the value of K is versus what the value of the law of mass action is at a specific point in the reaction. But you can also get information from the magnitude of K. So K, we kind of talked about this a little bit last time. K is a ratio, right? So that ratio is going to tell us the products to reactants. So if K is very large, like even 1 or 10 or 1,000, that means that the ratio of products to reactants is 1-to-1 or 10-to-1 or 1,000-to-1, right? So for every, if this is our K, for every 1,000 molecules of our product that we have left, we only have one molecule of our reactant left, right? So this ratio can tell us where the reaction goes to. Same thing if you have something that's smaller than 1, right? Let's say we have 0.1 or 0.001. Remember, that's a ratio too of products to reactants. So for every 1,000 reactants, in this case, we're going to have one product. So it can tell you the point at which a reaction stops. Now, this is a friendly reminder that it tells us the ratio of reactants to products, but remember, K does not tell us how fast our reaction gets to those products, right? We could end up hitting equilibrium with 1,000 molecules of products to 1 molecule of reactant in a millisecond, or we could get to that ratio in 1,000,000 years. We don't have that information. That would be a kinetic side of the equation. So K and rate are not directly related, but K is dependent on thermodynamic properties. So if you remember this graph, right, we have total energy, energy of reactants, energy of products. It leads us to a delta H, an overall energy change for the reaction. It also leads us, we can see our activation energy, so the amount of energy we need to get this reaction started and form those intermediates before the reaction can proceed. So the magnitude of K is actually related to the thermodynamic properties. And at the end of this chapter, once we go through K, we've already talked about how K is temperature dependent a little bit, but what we're going to go through once we get through chapter 13, we're going to circle back to the part of chapter 17 that we skipped so that you can see what that connection actually is between K and our thermodynamic quantities. So there is a relationship there, and we're going to explore that relationship after we kind of get through chapter 13. But for now, just realize that a connection does exist. We'll explore it later. And then you can kind of walk forward with knowing what the magnitude of K means for now. Okay, so the Q that we just talked about has a name. Q is going to be called reaction quotient. So it's the law of mass action plus any position. So remember, when we say position, we mean the set of concentrations that is not equilibrium. So you can be talking about initial concentrations, you can be talking at the final concentrations, you can be talking about the set of concentrations in the middle of a reaction. So any set of concentrations that's not at equilibrium, if you plug those into the law of mass action, you're going to get Q, the reaction quotient. Okay, and by comparing Q and K, you can decide which way this reaction is going to flow. And so actually, when you come across these problems in equilibrium, this is one of the first things you should do. You should consider, okay, what's my reaction? What's my law of mass action? And which direction will this reaction proceed? Right? Okay, so let's think through this. If Q is larger than K, what has to get bigger or smaller in order for Q to equal K? So what direction is that going to be? What does it mean if Q and K are equal? And what does it mean if Q is less than K? So this would be a good place to pause, take a stab at these answers, see if you can get yourself logically there, and then we'll talk about it together. All right, so remember, it's a ratio of, I'm going to get so sick of hearing me say this, products to reactants, right? So if Q is larger than K, then our fraction where it stands at Q needs to get smaller, right? So in order to get smaller, reactants have to get bigger, products have to get smaller. So that means your reaction of reactants and products, if reactants have to get bigger, then we have to shift towards the reactants. So that would be a shift left, right? We're running this reaction backwards as it's written. Okay, in the same way, what if Q is too small? So that means that fraction needs to get bigger before it can match with K. So products, the numerator has to get bigger, the denominator has to get smaller. So this would run the reaction to the right. It has to proceed forward. All right, so what does it mean if Q is equal to K? Well, then it's at equilibrium. And you're not going to see a net transfer or a net reaction in any one direction. You're going to have reactions in both directions at equal rates. It's that dynamic equilibrium. Okay, so calculating Q should be your first step, or considering Q versus K should be your first step, so that you can determine which way your reaction is going to proceed. And so this is what's going to make a difference in that change, right? This is what we were looking at in the last reaction. If you have reactants going to products, Well, your reactants are going to be being used. You're going to lose reactants and gain products. So that's this first case. Oh no, that's this second case. If we're third case. That's this third case. If we're forming products, K needs to get bigger. Products need to form. Your change for the reactants is going to be negative. Your change for the products is going to be positive. If your reaction has to go the opposite direction, well, then you're going to lose products and your change for the products is going to be negative. Change for the reactants is going to be positive. So this is going to help you, this relationship between Q and K, where you are now and where you need to go in order to be at equilibrium, is going to determine your change part of that equation. Okay, so for example, here we have a very specific context. We have the synthesis of ammonia. So that tells you what your reaction is. If we're synthesizing ammonia, then ammonia is going to be on this side, right? It's being synthesized, it's being made. I'm assuming this is the Haber process. So we're going to go H2 or N2, H2. This has to be 2, this has to be 3. Okay, so synthesis of ammonia. Here's our temperature at 500 degrees Celsius. Equilibrium constant they give to you. So K, we know already, 6.0 times 10 to the negative 2. Predict the direction in which the system will shift to reach equilibrium. Okay, so why do they give you temperature? They give you temperature just to show you that temperature doesn't change and you can ignore it, right? So, excuse me. They tell you your temperature is 500 degrees Celsius. You don't have to do anything to accommodate for that temperature unless the temperature changes. Now, the logical question that follows is, okay, so what do I do if the temperature changes? Well, we don't know yet. So nothing. Right? They're not going to change the temperature on you until they kind of teach you that part of the equation. And actually, I'll give you the technical answer right now. You never really have to do anything with the temperature. The most you're going to have to do with it is tell me relatively what the temperature change is going to do. So the most you're ever going to have to tell me with the temperature is is the temperature change going to force the reaction forward, or is it going to force the reaction backward? So you know it changes K, but by how much? You never have to figure that out. You're only going to have to talk about it in terms of relative changes, and we will get to that, but we're not there yet. So for now, they're not going to change the temperature on you, and you don't have to worry about it. All right, so let's figure out these cases. Case A, go ahead, figure out what your Q is, relate that to K, and tell me, is this system going to shift towards products or towards the reactants? Pause it and try that now. Okay, in this first case, I got a Q of 1.25 times 10 to the 7th. So 12,500,000,000. No, 12,500,000. There we go. Either way, it's a lot bigger than K. So Q has to get smaller. So we're going to have to decrease products, which means we're going to shift this one to the left. This one will shift to the left in order to reach equilibrium. Okay, now I'm going to do B. All right, I got 6.0 times 10 to the negative 2. Well, look at that. That's at equilibrium. So it's not going to shift anywhere, right? I'm already at equilibrium. The rate is going in this at the same rate in both directions. So it's not shifting anywhere. There you go. So now we have the ability to calculate Q, compare it to K, figure out which direction the reaction's gonna go. All right. Okay, so now we get into the fun stuff. All right, so here's what's about to happen. We're about to look at K from a bunch of different angles. So we've already talked through basically all the concepts in this chapter, right? What is equilibrium? What is K? How is it used? Okay, but now we're going to look at this through a bunch of different contexts. So every time you approach these kind of problems, here you kind of want to do it systematically, because the trickiest part of these problems is figuring out what you have, where you're going, and how to start, right? So the first thing you want to do is you want to take into account everything you have and really figure out what you're going. So as we're doing these problems, I want you to try to annotate, underline things they give you, circle what you're trying to find, identify that one word that you're trying to find, and that will help you figure out where you're going. Also, by underlining information or by writing it on the side in a list, you're going to have a really good idea of what you already have. Okay, so let's just process through these. Another good way to do this is 2 more considerations, and then we can start. First of all, pause it. See if you can beat me there. Second of all, when you get stuck, see if you can formulate a question and get yourself unstuck. Remember, understanding what I do and being able to do it yourself are 2 different levels of understanding. So if you get stuck and can formulate a question, that's a really good place to be. If you understand what I do, that's great, but you need to keep doing it. You need to practice it until you can do it from start to finish with just a periodic table and a calculator. right? So evaluate where you are in your understanding and don't lie to yourself. Don't allow yourself to lie to yourself. You're more valuable than that. Okay? So be honest about where you are. Understand mistakes are going to help you learn. And by being honest and taking the responsibility and doing this practice until you can do it, start to finish, that's really what's going to carry you into the highest level of understanding on these. Okay, so try this problem, pause this, do your best, get stuck, ask a question, and then unpause and see if I have the same approach as you or a different approach. Okay, here we go. Dinitrogen tetroxide in its liquid state used as one of the fuels on the lunar lander for the missions. Interesting. In the gas phase, it decomposes to gaseous nitrogen dioxide. So here's a reaction for me. Consider an experiment in which gaseous N2O4 was placed in a flask, allowed to reach equilibrium at a temperature where Kp equals that. Okay, so we have a K. At equilibrium, the pressure of N2O4 was found to be 2.71. Calculate equilibrium pressure of NO2. So that's what I'm looking for. All right, so let's take a minute and figure out what we know. So N2O4, 2NO2. Okay, initial change equilibrium. So we know what the Kp is. Kp is going to be NO2, the pressure of NO2 squared over the pressure of N2O4 to the first, and that is equal to 0.122. All right. Then they give us the equilibrium pressure of N2O4 at 2.71. They want us to find equilibrium pressure of NO2. Gaseous N2O4 was placed in a flask, allowed to reach equilibrium. So that means initially we had none of this, and we don't know how much of this we have. Okay, so all we want to find is the equilibrium pressure of NO2, right? Well, we can't get that from our ice chart. We just don't have enough information. We don't even know what we started with N2O4. But we do have a Kp equation. So I know I'm going to have some amount of NO2, and I'm going to square that amount, right? If this is X, I can call this X. And I'm going to have 2.71 of N2O4, and that equals 0.122. So all I have to do in this case is solve for X. Let me do that on my terrible calculator. .33062. Let's take the square root of that. And I get X equal to 0.57. How many sig figs am I keeping? 5 ATM. 0.575 times 0.575. I'm just verifying my terrible calculator. Yep, that works out. All right. Okay, so pretty simple problem there, but the ice chart helped me organize my thoughts, and then I relied on the K. So having a reaction written out from the beginning is a good idea. Having a K equation written out from the beginning is a good idea. Organizing your thoughts and information into an ice chart is a good idea. Let's try to do those three things consistently. All right, we'll do this one together. We'll practice this one together in class. Okay, number 2, we're going to find the change in equilibrium, finding K. So again, a good place to pause, try it, unpause, see if I approach it the same way you do. At a certain temperature, a 1 liter flask contained this many moles of PCl3, this many moles PCl5 after the system had reached equilibrium. This many moles of Cl2 was found in the flask. Gaseous PCl5 decompose according to the reaction. Calculate equilibrium concentrations of all species. So we're looking for equal concentration. That's what we're looking for at equilibrium for all species and the value of K. All right, so we're looking for two things. So I know what my reaction is. I know I can write a K equation for that. They're all gas. So Cl2, PCl3, 1 and 1, PCl5, also a 1. All right, let me write this equation out. So I can use an ice chart. What do they give me? 1 liter flask initially contained, okay, so all of these 0.298 moles divided by 1 liter is going to give me my term in molarity. So I'm going to do that. 0.298 molar. Oh, that's PCl3. All right, and none of this, after the system had reached equilibrium, they tell us that 2 times 10 to the negative third molar was reached. Okay, calculate equilibrium concentration. So they don't give us K in this instance, so we have to approach this differently, but they do give us a lot of information for our ice chart, including the initial and equilibrium concentrations of one thing. If I know initial and equilibrium of something, I can tell you what the change is, right? The change had to be the difference, 2 times 10 to the negative third molar. And if I gained that much of Cl2, I also gained that much of PCl3, and I also lost that much of PCl5. All right, let's break out the hopefully more trusty than mine calculators. All right, here are my equilibrium concentrations. And because I change into molarity from the get-go, it's already in concentrations. That is something I would recommend doing. If you can change into molarity in the beginning, do it. Because K is in terms of molarity, right? And if you don't do it in the beginning, chances are you're going to forget to do it. Now, this problem is forgiving, because if you forget to do it, your amounts are going to be the same, but they're not always that forgiving. All right, now let's figure out what K is. There we go. There's our K. So we now have equilibrium positions in K. Again, notice our K equation helped us. Our ice chart helped us. We want to rely on these things. Okay, if you had questions, if you got stuck, take a minute, pause the video, jot those questions down. You don't just want to look at this and be like, oh yeah, now I get it, right? see if you can formulate a question. See if you can go find more practice. The back of your book has tons of practice. Do the problems in the back of your book. That will give you a lot of the practice that you want to find. All right, here we go. Using variables. Ooh, that should make you shiver. Variables, we love them. Okay, so again, same problem from a different angle. Let's try this. Pause this, see how far you can get. I've already kind of shown you how variables can help. See if you can get through this problem solve through this question. All right, carbon monoxide reacts with steam, produces carbon dioxide and hydrogen. 700 Kelvin, equilibrium constant is 5.1. Calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. Okay, so we need a reaction, we need a K, and then we need to figure out numbers that fit inside that and the ice chart. So carbon monoxide reacts with steam. Both of those are gases. Carbon dioxide is a gas. Hydrogen is a gas. So everything's going to be in my K equation. Let's balance this real fast. Oh, it is balanced. Okay, and they tell us our K is also equal to 510. So 1 mole per liter gives them all a 1 molarity. Each component, that means all of them, C and E. All right, so there's my initial amount, but I'm not at equilibrium and they don't give me information about equilibrium either. So we have to figure out what direction this is going to shift. So what's my K, or my Q? My Q is going to be 1 times 1 divided by 1 times 1, which is 1. So Q is going to be smaller than K. If Q is smaller than K, then I need more products to make it bigger. So this is going to shift forward. So that means I'm going to use products, and I don't know how much I'm going to use, so I'm going to use a variable. I'm going to use reactants. I'm going to gain products. 1 minus x, 1 minus x, 1 plus x, 1 plus x. Okay, so now I'm going to use my K equation and figure out what these x's are to figure out an actual amount at equilibrium. Okay, now I'm going to have to solve. So 1 plus x times 1 plus x, I'm just going to do squared. 1 minus x times 1 minus x, again, I'll just do a square, equals 5.10. Okay, so now we need to solve for our x. Square root, square root. So this whole expression becomes 1 plus x over 1 minus x equals the square root of 5.1. .25 ugly decimal. Okay, so I'm just going to keep that in my calculator and just write it as the square root of 5.1 because that's faster. Okay, so now I have to solve. So I'm going to take what's on the bottom here and swing it to the top. 1 minus x, so I get 1 plus x equals square root of 5.1 minus the square root of 5.1 x. All right, so let's subtract x from both sides. And let's add, no. Subtract the square root of 5.1 from both sides. All right, now we do have to deal with it. All right, so 1 minus the square root of 5.1 equals, I'm running out of space. Okay, 1 negative 1.258 equals, I should have done it the other way. Oh well, negative 3.258 x, divide both sides by negative 3.258. So that should be 0.386-ish equals x. Whoo! Yeah, algebra. All right. 0.386 equals x. So now I can go and figure out what my equilibrium concentrations are, because x is not my equilibrium concentration, right? I have to go 1 minus x or 1 plus x. So this is, how many sig figs am I keeping? 3? Okay, 1.39, 1.39, and this is going to be about 0.614, 0.614 molar, because we're talking about concentrations. Okay, did I do what they asked me to do? This is reason number 2, to circle and underline, because by the time you get through all of this, I usually forget what they actually asked me. So I need to calculate equilibrium concentrations. Oh, I did that. Awesome. So I'm done. Woo woo. There we go. All right. Using x. It's a variable. It's definitely your friend. Again, if you watched this and you understood what I do, maybe erase your work and try it again, or come back to it the next day and try it again, or look in the back of the book, see if there's more practice and try it again. Go start to finish, see if you can get there. Okay, this is a good place for us to end for today. What we need here is just practice, 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 practice. So we're going to come back together. We're going to do some of this practice together. You're going to ask awesome questions. You're going to keep practicing, and eventually it's going to click. I promise you it will, but you have to keep trying. Okay, so let me know what questions you have. Definitely jot those down. I will see you in class.